Hello and welcome to the section of the MATLAB tutor. Here we're going to continue talking about complex numbers and just giving you some practice with how MATLAB deals with complex numbers and imaginary numbers. So first we'll just recap. Imaginary number, as you know, is the square root of a negative number. So if we actually calculate and ask MATLAB what is the square root of -1, it's going to respond with I. If we ask MATLAB to ask us to answer what is the square root of -8, then it'll tell us 2.82i because it takes the square root of 8 and then it knows that it's got to be imaginary because it's a negative number. In fact, if you take the negative out, MATLAB's going to respond with 2.8284. So that's all doing exactly what we expect MATLAB to do. And we also said, of course, you can assign variables, 3 plus 3i. We could do a variable b. Let's call it 5 minus 9i. All right. And in addition to adding and subtracting and multiplying, dividing these complex numbers, we can do things like raise them to powers. We could say a to the power of 2, a squared. So that's going to be like taking a times a. In fact, we'll do a squared and we'll get the answer 18i, and we'll tell it, I'll go ahead and compute manually a times a, which is this complex number there. So whenever we do this guy, that's the same thing as saying 3 plus 3i times 3 plus 3i. So what MATLAB's doing behind the scenes is distributing and multiplying every term times every other term. Anytime you get I squared, you're going to get -1 because I times I is -1. I times I should always give you -1. That's something you learn about when you deal with complex numbers. And so there's cancellations going on, and so the answer that MATLAB computes is all correct and follows the rules of complex numbers as you might expect. So you can also do things like raise things to a negative power. So this b to the -3 would be, and b, by the way, is given, we've already defined it, 5 minus 9i. So when you raise it to a negative power, it's like saying 1 over b cubed. And it does all that math for us, and so we have a very small real part, -9.15 times 10 to the -4. The imaginary part is also very small, -4.53 and so on, times 10 to the -5. So it does all that stuff behind the scenes, which is great. We can actually do things like taking a complex number and raising it to another complex number because a and b are both complex. And when you do that, MATLAB does all the heavy lifting and computes the answer. So it behaves much like a calculator. You might expect a high-end calculator to do. Now, another thing is there are a lot of built-in functions in MATLAB that are specifically designed to basically operate on complex numbers. One of them is the absolute value. The absolute value, as you know from basic algebra, of -4 is just 4, right? But this absolute value function also works just fine on complex numbers. So this is a complex number. A is 3 plus 3i. So what it's going to do is calculate the magnitude of this guy, and it'll always respond with a positive number. So what's going on here, if you look into the math behind it, is you're doing the Pythagorean theorem on the real part and the imaginary part, and you're getting the answer, and that's what we call the absolute value, or the magnitude of that complex number. Now this complex number lies in the complex plane as well. You have a real part and an imaginary part, so there's always an angle defined with every complex number, the angle from where you are to the x-axis. So to pull that angle out, you just basically type in angle and then you pass it the complex number and it's going to respond with an angle. Now, you should know by now, MATLAB always deals in radians, so this is an angle in radians. If you wanted that to be in degrees, you would say, okay, let's take what we did before, take the angle of that complex number. We need to multiply it by 180 divided by pi. That's going to cancel radians with radians, and so you're going to be left with degrees. That's just a conversion factor, so that's 45 degrees. And that should make sense to you because the complex number a is 3 plus 3i, so it's 3 units over on the real axis, 3 units up the imaginary axis. It should be right at 45 degrees, and that's what we get. Okay, so doing the absolute value of a complex number and the angle that exists in the complex number is something you'll be doing a lot with anytime you deal with any kind of complex results. The other thing is I just want to show you that you can, this absolute value business, makes intuitive sense if you just operate on pure imaginary numbers. I mean, there's no real part to this at all. So the absolute value should be 2. All right. if you have 3i, the absolute value should be 3, and so on. So if you pass it a complex number to plus 3i, then like I said before, it's doing the Pythagorean theorem to find out what the magnitude there is. Same thing for the angle, just to kind of review a little bit. If you have a pure imaginary number, see, it's a pure imaginary number. There's no real part to it. It's just imaginary. So the real part is 0. The imaginary part is straight up and down on the imaginary axis. So the angle for something like this is always going to be 90 degrees, or pi over 2. This is pi over 2 radians. And if you didn't believe me there, you could just multiply by 180 over pi, which is our conversion factor, and that's 90 degrees. So any kind of pure imaginary number when you're trying to find the angle is going to give you that. So whenever you do something like angle B, which is over here we have 5 minus 9i, then what you're doing is you're basically taking the inverse tangent of this divided by this. That's all given in your math books to find that angle. In this case, it's negative blah, blah, blah radians, and you can multiply by 180 divided by pi to give you the angle in degrees. So it's almost negative 61 degrees would be the angle where that complex number lies. All of this stuff is taught to you when you start learning about complex numbers. I'm just kind of going through some real calculations so you can kind of get familiar with how you deal with it in MATLAB. Now, you also have some other functions that are designed specifically to deal with complex numbers. For instance, there's a function called real, and if you pass it something like this, then it's going to return whatever the real part of this is. So this is the real part, this is the imaginary part, so it's going to return 3. Right? Of course, it's perfectly happy if you if you put a variable in there that has a complex number, right? 5 minus 9i, that's what I'm putting in there, so the real part of that is 5. So it's just going to return this guy. The same thing works just fine with imaginary. If I stick the variable a into the function called imaginary, imag, then this variable is going to go in there. The imaginary part is 3. So the imaginary part is going to return 3. If I stick variable b in there, if you look at what b is, the imaginary part is negative 9, so it's going to return with negative 9. These are things that really are not so much that you would probably not do them so much when you're just working with these basic complex numbers, but you might use them a lot if you're programming in MATLAB. Maybe you're writing a function that you've got a very long calculus, integration or something like that you're doing, the result of which might be complex, right? Well, then your final answer, maybe you want to strip away the imaginary part and only give yourself the real part in the final display of the answer. Let's just say whatever integral you're doing, you only care about the real part of the result. So you might have a function in one of these .m files that calculates the integral, it gets a complex answer, and then you might at the very end just take the real part of it and display the real part as the answer. Maybe that's just your algorithm. So these functions, real and imaginary, absolute value, angle, things like that, those are things that are kind of trivial, but you might use them when you're programming, so that's why we're really covering them. Okay, let me clear the screen. Finally, before I close here, I'd like to just kind of go over some things, something very important with complex numbers that you learn in your math classes in trigonometry and in calculus in specific. So if you remember, there's something called the Euler identity, right? And that means that if you have a complex exponential, right? For instance, something like pi times I, okay? So this is a complex exponential. In other words, it's e raised to the power of pi times I. And if you have learned about the Euler identity, which most of you probably have, then what it means is that this is an equivalent way of writing a complex number. The magnitude of this guy, remember the absolute value we're just calculating, is whatever sits out in front of this exponential, which in this case is 1. The angle, which remember we were using the angle function, is basically the angle here that sits in front of the I. So I can just look at this without doing any calculations, and I can see that the magnitude, the absolute value of this complex number is 1, and the angle is pi. And that's just because of the way it's written here. Now, whenever you deal with complex exponentials, sometimes you want to convert them back and forth from polar form like this, or I guess complex exponential form. You might want to convert them to rectangular form. So when you type it in like this and you hit enter, MATLAB is going to basically automatically convert it to rectangular form. So MATLAB says that from the Euler identity, from the math behind it, this is equivalent to -1 plus 0i. In other words, it's equivalent to saying the real part's -1, the imaginary part is just 0. And so that comes about because the Euler identity is cosine of the angle plus I times the sine of the angle. The angle here is pi. So cosine of pi is -1. Okay, that's the real part. Plus I times the sine of this angle, and the sine of pi is 0. So that's cosine plus I sine of the angle, and that is the Euler identity, and that's why you get this. Now, if you were to just take the absolute value of exponential pi times I, and so basically this e to the pi I, you wrap it inside of the absolute value function, what you should get is the absolute value of this complex number, which we already said. The absolute value, when you write it like this, you learn from your math, is just whatever sits out in front of the exponential, which is 1. So the absolute value, which is the magnitude of this complex number, is 1. So let me go back and change the function. Instead of absolute value, what if we type in angle? What we're trying to find here is what is the angle that this complex number sits at? Well, the magnitude is what sits in front of the exponential. The angle here is the angle in radians that we have. So if you hit this guy, then what you're going to get is 3.14. That's pi. So I'm just telling you in a roundabout way that MATLAB understands Euler's identity. It understands all of the identities, basically. So if you type a complex number, complex exponential in, MATLAB is going to convert it to rectangular for you. If for some reason you would like to extract the magnitude and the angle, it totally understands if you put them in complex exponential form. It'll give you the absolute value. It'll give you the angle back. Or if we, like we did in the last section, if you put these guys in rectangular form, like we did in the last section, it understands how to calculate the absolute value and the angle. So sort of the bottom line to take away from this is MATLAB completely understands, no matter how you enter your complex number, how these functions that operate that return magnitude and angle, it understands how to do all the calculations behind the scenes. One final example. Let's say that, for instance, I want to take the absolute value of the complex number, but let's define it as a complex exponential. 3 times the e to the power 0.4 times I. So this is a complex exponential here. 3 times e to the 0.4i. You know, this is the complex exponential way of writing a complex number. And you can convert back and forth between the complex exponential representation and the rectangular representation. But MATLAB understands that the absolute value is basically the number that sits out in front, which you learn in your classes. So the absolute value is 3. When you go over here, if you take away the absolute value and ask it to return the angle, it understands that the angle of this complex number is whatever is sitting out in front of this I. So 0.4 is what gets returned there. Hit enter one more time. 0.4 is what gets returned there. So again, the bottom line is no matter how you enter your complex numbers, if you hit angle A, so this is a rectangular form that goes in there, MATLAB understands, okay, calculate the angle. It's in rectangular form. Here's the angle in radians back. If you're entering complex numbers in complex exponential form, it understands that. It understands all of this stuff. So you don't have to worry about how should I convert it, how should I present it to MATLAB. It understands all that stuff. If this is foreign to you, if you don't understand what I'm talking about by complex exponentials, it just means that it's something you've forgotten, or it's something in a math class that maybe you haven't taken yet or haven't used that much. This is just another way of writing a complex number that is used quite a bit in math. So when you're working with MATLAB, you can use any representation you can. MATLAB understands all this stuff. Get it out, play with it, practice with it, and get comfortable with how to use complex numbers, including the Euler identity in MATLAB.